solution. Going twice. What? Yes? 23? Sold! Start with that. 23. Is it the giant one? Has a whole bunch of stuff, like 2 times the x plus 1 quantity cubed? Yeah, okay, gotcha. This is a fun one. You're like, no, it isn't. That's why I asked you. And I'm like, yes, it is. Math is fun. Or it can be 2 times x plus 1 quantity cubed times x plus 5 over x minus 3 quantity squared times x plus 2 quantity squared. Oh my dear God, that's a lot. And the function kind of looks like this. Like that. What does it want us to do? Find vertical asymptotes, horizontal asymptotes, and the limits. Okay. Groovy. How do I find vertical asymptotes, guys? Vertical asymptotes are when what happens? Anybody?
Is it something over 0?
Yes, something over 0, specifically any number other than 0 over 0. So let's start with the denominator. What makes the denominator go to 0, guys? X equals what? And x equals 3 and negative 2. Now, do either one of those make the numerator also go to 0? No, so both of these are vertical asymptotes. Congratulations. You've just found those. This and this right here. So here's x equals 3, and here's x equals negative 2. That was fun. How do I find horizontal asymptotes?
Zero over 0? No.
No, that's holes. Think chapter 9.2.
Highest power.
Thank you, highest power. We take the limit as x goes to infinity. That's what we do. And when we think infinity, we think x to the highest power. So the highest power terms survive, which is what? Cubed. Are you sure?
Yeah.
You sure? If I were to cube this out, this would be x cubed, right? And then the leading term here would give me x to the what? What's x cubed times x? Oh, thank you. So we basically have a 2x to the 4th going on uptown, right? Because this is going to be 2 times some x to the 4th. You guys with me? What's the highest power downtown? X squared times x squared is x to the 4th. So my highest power terms are going to yield me a 2 over 1 equals 2. And that is my horizontal asymptote, which would be right here. Y equals 2. Questions? Yes?
What's that under the infinity?
Under the infinity, x to the highest power, not horsepower. Although that would be fun. I don't know how you would quantify that. What is a horsepower anyway? Anybody, cars? Anybody into cars? I should know because mechanical engineer, but I don't because why would I? Does anybody know what a horsepower actually is or how that like translates to newtons as a force?
Nope.
Anybody? I guess I could. Horsepower to newtons. I'm gonna look that up.
1 horsepower equals 20 newtons.
Yeah, equals 1 newtons. Yeah. Or is it like kilogram newtons? I don't remember. Not my wheelhouse, not anymore. Does it make sense? Yeah? What was the hard, yeah,
Sorry, I know
It's
I
okay.
missed last class, but you basically just solved the top and then solved the bottom to get that, and then these two overcomes, right?
I didn't just solve the top and the bottom, because what I did was I understood that this is gonna give me an x cubed. So I did a lot of cheating, essentially. If I'd foiled this out, it would be a nightmare, it would be several terms long. But I'm not gonna do that. I know the leading term here is gonna give me an x cubed times x gives me x to the fourth. The 2 is gonna come along for the ride. My leading terms here are gonna give me an x squared. Leading term here, x squared times x squared is x to the fourth. Its leading coefficient is 1.
So you're just taking the leading coefficient and the exponent.
I'm taking the highest power x and the coefficient to those highest power x's. So the highest power on the numerator is x to the fourth, the highest power on the denominator is x to the fourth. The constant coefficients to those terms survive. It may not be the leading coefficient, because your highest power may be buried several terms deep. Does that make sense? It could look like this.
Oh, so it's just the coefficient in front of that power.
Right. Where's your highest power?
Side. The fifth.
Yeah, so my highest power is to the fifth. So the leading coefficient when I look for horizontal asymptotes or taking the limit to infinity is gonna be 6 over negative 5. So there will be a horizontal asymptote at negative 6/5 on this function. Yeah. Okay. Any more questions on this one? Yeah.
Is there a rule where, like, I remember there an example you gave us last class. It's kind of like this, where there's a 4 and a 5, and you would pick the highest power, but not multiply it by a second term or anything like that.
What do you mean not multiply it by a second term?
Like you're doing like x plus 1 to the third, and then
Mhm.
multiplying it by x to make it x to the fourth.
Mm-hmm.
But over here, you wouldn't do that.
No, because this is the foiled version of whatever this is. I could factor this out. This has already been factored for your convenience because the book is not that evil. As scary as this looks, it actually did you a favor because you don't have to factor it to find your vertical asymptotes. You don't have to figure out what x values make the denominator go to 0. So they factored it for your convenience for this step. But unfortunately, knowing algebra is what it takes really to be able to do the horizontal asymptote. You have to know that if you foiled all this out, your leading coefficient would be sum 2x to the fourth. And if you foiled all of this out, your leading coefficient would be 1x to the fourth. Okay? Okay. Anything else on this one? Yes?
Sorry, one last thing. For the vertical asymptote, you got 3 and -2 from the bottom,
Yep, I sure did.
and you just flip the signs, right?
It's not so much flipping the signs, it's what makes any term go to 0. Because 0 times anything is 0, and then what makes a vertical asymptote is a non-zero numerator and a 0 denominator. So I'm not flipping the signs so much as I'm saying, if I plug 3 into this, I get 0 for this term,
Oh, okay.
okay? And if I plug -2 into this, I get 0 for this term. Okay? All right, yeah.
So then if one of those, either x equals 3 or x equals -2,
Mm-hmm.
if we were to plug that in on the numerator, it would be 0 over 0, that
Nope.
would not be included, that would be a whole, or?
That would be a hole. If you were to plug these numbers into the numerator and get a 0, there would be a hole at those x values.
Okay,
But no hole this time.
great, thank you.
Yeah, you're welcome. All right, you guys. Let's tackle the pollution problem. That's a fun problem, actually. That would make me anxious. Just like, I can't get any higher. I must hit talk. Or whatever it is. Sorry. All my sounds are so calming. My husband's like, your alarms, I would sleep right through. I'm like, I know. That's why I like them. They don't wake you up, but they wake me up. Because the second he wakes up, he like grabs me. And I'm like, I oughta pee. It's cute, but it's annoying. Like I'm hot and I need to pee. Let go. Pollution. Oh, good times. Such good times. So we're doing, I'm assuming it's 100C over 7,300 plus C, whoever asked for this one?
I believe so.
Okay, awesome. So P equals 100C over 7,300 plus C. Where P is the percent of pollution that can be removed. Definitions matter here. And C, I'm guessing, is the cost of removing said pollution. I'll double check that. Okay? So that by spending C dollars, yeah, okay. C dollars is cost. Describe any discontinuities and explain which each discontinuity means. That's not what it asks. Find the percent of the pollution that could be removed if spending C were allowed to increase without bound. Can 100% of pollution be removed, and explain? So how much of the pollution could we remove if the costs were allowed to expand without bound? So don't look at the math and just tell me. If I could spend all the money in the world, could I make the pollution go away?
No.
Yes, I could. If I could spend all the money in the world, I could make it absolutely pure, okay? But there's a problem with that. Is that reality?
No.
God, no. The reality, and some of you aren't gonna like this, but it's reality. The reality is the EPA has set fines so low that for most polluters, it's cheaper to pay the fine than it is to actually clean the air. So until we hit polluters in their pocketbooks, they're going to continue to do it because it's cheaper for them to pollute and pay the fine than it is to actually clean the air that they're polluting. Good times. All right, so that's the top and bottom of this. In reality, we cannot remove all the pollution. If we could spend all the money in the world, we could remove all of the pollution, right? So that's the intuitive thing we know about this. Now let's use the math to prove it. It said, how much could we remove? What percentage could we remove if costs were allowed to expand without bound? So where's cost going to? Infinity. We are literally taking the limit of this function as x approaches, or c in this case, since that's our variable, c approaches infinity. So what's our highest power? C to the what? 1. So this term will survive, and the 1 in front of here will survive. So we just proved using math what we knew intuitively. If we could spend all the money in the world, we could remove 100% of the pollution. Does it make sense? Yeah. Yeah. I see the hand sort of like creeping up your face. What's up?
How did you get 1?
How did I get 1? What's the constant coefficient right here? Yeah. So those are the terms that survive because they contain the highest power. Does that make sense? Now, what's the second part of that problem? Can 100% of the pollution be removed? No, I can't. Because you can't increase costs to infinity. If you were a business, you would have to figure out what's the most cost-effective thing for you, and that's why polluters end up polluting, is because it's cost-effective to do so. Okay? Make the fines higher, or, get a little closer to the world cooking itself, and we will start to care a little bit more about the pollution. But really, we're not gonna care about pollution, we're not gonna care about climate change, we're not gonna care about our seas rising until it hits us in our economic home. And that's the sad reality of it, guys. I know you were an entire generation that was raised on the fact that climate change is looming. So was I. We didn't act. I don't know if your generation's generation in front of me, the boomers, well, they're just hosed. They're all like, we're retiring, fuck all y'all. That's pretty much where they are. And that's the truth. It's kind of where they are as a generation. Individually, it's not like that, but That's kind of where they are. So it's just a mess, right? So I can put, if I chose to, I could put politics, I could put environmental policy, I could put all kinds of stuff into this class, but that's not my job. I'm just telling you that math doesn't exist in a vacuum. This kind of thing has ramifications outside of the classroom, outside of the university, outside of Denver, okay? This tiny little function gives you a little glimpse into what businesses do for their bottom lines. Okay. Questions? And you're like, no, we're good. Really, questions? We're gonna do something different today. We are exiting the world of limits, mostly, and entering the world of derivatives today. So raise your hand if you've had some kind of calculus before. Anybody in here? Anybody? Anyway, okay, this is, yes, one person. It's gonna be all new to the rest of you. Good times. Here we go. Take the shirt off. It's kind of get sweaty. Hike up pants. Pull down the shirt. Okay. Shut that so it's not distracting me. This is the most fun I can have in this class, you guys. Seriously. This is 9.3. 9.3. The derivative. So we have some function. Now, whether you've taken finite or you've taken college algebra at this point should be irrelevant for this section. Mostly. Because you will have seen something. How many of you took finite? Oh, you're gonna groan real soon. How many of you took college algebra? Okay, you guys might take a little longer to groan, but get ready. And you're like, oh, this already doesn't sound good. If I pick an x value, let's just call this x. It has a corresponding y, doesn't it? Over here. Because we all know that if we plug an x into a function, we get out a, that's right, we get out a y value. Damn straight. What if I plug in another x? I'll get out a similar y. Right? Everyone cool with that?
Yep.
So, if I drew a line between those, that would be the average rate of change, or the AROC. Because I'm lazy. AROC is average rate of change. It's literally over this domain, how much did your range change? Right? If over this x distance, how much did y change? Did it go up? Did it go down? By how much? Right? That's average rate of change. The thing is, average rate of change has another name. Anyone know what it is? Slope? Slope. Right? Slope. Also known as M. Also known as change in y over change in x. Also known as rise over run. We have so many names for this. I'm writing them all up there because one might like ting in your brain. Also known as y2 minus y1. We did this day one, remember guys? x2 minus x1. So here's one of those algebra skills you're going to want today. Okay. So write these y's over here? It's okay, you can just put it next to it. You know, I heard that. Who's writing in pen that's hating me right now? You know they make erasable pens. What? Yeah, you heard me. Make erasable pens. Isn't that genius? I have some if you want them. I don't like them. Let's call this f of x. Okay? Because we plug x into the function, we essentially get out a y, which is f of x. I know that seems crazy, but it is what it is. And I'm going to define the distance between these as h. You guys with me? Yeah? No? Oh, hell no. So if this is x, and this is h, what's all this?
X plus H.
X plus h. Isn't it? So what are we plugging into the function to get out a y value here now? X plus h. And you're like, I don't like that sound. I do though. It's so much fun. So if I were to write this slope using those terms, let's see what that would look like, shall we? So we have y2, which is f of x plus h, right? F of x plus h, minus y1, which is f of x. This is starting to look familiar. You guys don't like this, do you? Yeah. Okay. Over x2, which is x plus h, minus x1, which was just x. What's x plus h minus x? Simplify to, guys. H. So this is now f of x plus h minus f of x divided by h. Raise your hand if that looks even vaguely familiar to you. You don't have to remember what to do with it. Just get it up there if it looks anywhere. Okay, good. You're hating me right now, aren't you? Because you hated these, didn't you? Yeah.
I actually found them to be quite enjoyable.
I'm gonna throw something at you soon. It'll be a candy bar or something, because I'm happy that there's someone out there that's enjoying this, but for everyone else, it's pretty painful. So you and I are like simpatico, but everyone else is like, no, not so much. So, all right, so we've got this slope, but that's just the average rate of change. That's just the slope between 2 points. We're gonna do some fun crap to this thing. Are you ready? What's gonna happen to h if I scoot this x plus h this way a little bit? It's gonna get bigger, smaller, stay the same? Smaller. The value for h is gonna get smaller, right? Likewise, this little point will move with my x. So if my x is here, my point's gonna stay with it. And if I drag it this way, my point's gonna get closer and closer and closer to what? X. So if I take h to 0, these will sit on top of each other, won't they? You ready? Okay. I love this stuff so much. So all I'm doing is I'm crashing those 2 points like cars together. So I'm taking h and I'm making it go to 0. I'm taking this distance here and I'm making it go to 0. So what was an average rate of change between 2 points becomes something else altogether. It becomes the instantaneous rate of change at a point. So this is the one I want you to write out. Instantaneous. I can spell instantaneous rate of change. What the hell does that mean? Anyone want to take a stab at it? Is there a smack stick in here? Nope.
yardstick.
Oh, it's not. But this will work with my yardstick. So I am making a slope that is unique to this x value. If I drag this x value anywhere, my slope is going to change, isn't it? You guys with me? Okay. What kind of slope do I have right here? Let's find out. Let's drive at it. 0. What kind of slope do I have up here? 0. So you guys can see that intuitively, right? Congratulations, you're doing calculus. This is it. This is as hard as it gets, guys. This is the definition of the derivative. All we're doing is taking two Gesundheit. We're taking 2 points on the same function and we're smashing them together. And the resultant slope is how much this function is growing at that particular point. So here it's bottomed out, it's not growing at all. Here it's topped out, it's not growing at all. Here, the slope is getting steeper in the negative direction, right? It's just continuing to curve down like this until eventually it's just gonna go, you guys with me? Here, it's continuing to grow in the positive direction, so eventually it's just gonna head straight up. Eventually, I mean, we're not sure, but that's my guess. How do you guys feel about this? Visually, does it make sense? Who's taken calculus before? Did they ever explain it this way? Does it make sense? Did it make sense before?
A little bit.
Awesome, okay, so slight improvement, great. Yes,
What do you mean by the slope is 0?
the slope is 0. I'm saying, is it growing, shrinking, or not changing at all at that point? So think about a corresponding slope for any given point. It's shrinking here, it's shrinking, but it's getting closer to 0. It's 0.
Because the slope is always like a straight line, but.
The slope is a straight line, yes. The slope is a straight line.
that's following the curve.
Yeah, so this is comprised of an infinite number of slopes, right? If I were to just draw a whole bunch of, like this. If I were to just draw a whole bunch of lines, like so, it would approximate a curve eventually, wouldn't it, guys? So this is just a bunch of slopes at a point, and you do enough of these and you get the feel of the curve. So far, so good? It's nice. The devil's in the details. The devil's in the details because you actually have to do stuff with this. This is good for all functions. Good, big ones, small ones, little ones, tall ones, doesn't matter. Yeah?
Is that like dotted arrow that's going that IROC, is that supposed to be like the slope for that dot?
That is the slope for that dot. Yep. So think of a circle. Up here, there is no slope, right? You could balance this if I were to catch it right. So at that particular point on the circle, there is no slope, right? On this particular point of the circle, there is no slope. On this particular point of the circle, this is an infinite slope because it just goes straight up in the air. Infinite slope. Everywhere else, it's negative or it's positive, right? It's negative or it's positive. We always read them from left to right. We actually don't use circles because they're not functions. We don't do unfunctions here. That's regular calc. How do you feel? Better? So let's look at the devil in the details. Let's take a look at this. I'm going to do a simple problem like x squared plus 5. And we're going to work this out. definition of the derivative to find f prime of x, which is like saying the derivative, when f of x equals x squared plus, what did I say? 4? 5, 4, doesn't matter, it's not part of the derivative. That's okay, let's go with 5. So I've defined my f of x. That's what this is right here, f of x. That's my function. Now I have to create f of x plus h. So what was my input here? Plug a what in? An x. What's the input here? So anywhere I saw an x in the original function, I'm going to substitute x plus h. Okay? It's just like saying instead of 4, we're going to do 4 plus 2 is 6. So it's a different value. We're just plugging it in for the valueless thing, the variable, right? So f of x plus h is x plus h quantity squared plus 5. So instead of inputting x and squaring it, we're inputting x plus h and squaring it. So far, so groovy? That's not so bad, right? Okay. Except I need to FOIL this out now. X plus h, zoom type, times x plus h plus 5. Do you guys remember FOIL?
Yep.
Raise your hand if you have no idea what I'm talking about. No shame, it's cool. Seriously. So you guys all remember what FOIL stands for?
Yep.
All together now? First, outside, inside, last. So if I FOIL x plus h times x plus h, what's my first term? X squared. And what's my outside term? And what's my inside term? Which I'll just make xh because that's fun. And what's the last term? Good. And we're still adding 5 to the end of that. Can I collect any terms? Can I group any terms? So what's 1xh plus 1xh? 2xh. Okay, so I have x squared plus just 2xh plus h squared plus 5. And this is my f of x plus h, okay? So now I have everything I need to plug into this formula. So let's do that. Switch to another color here for that. So we're doing the limit as h approaches 0 of f of x plus h, this beast. So I'm going to parenthesize it just for giggles. X squared plus 2xh plus h squared plus 5 minus f of x. I'm also going to parenthesize that. Can anyone tell me why? To distribute the negative, because that 5 needs to go negative too. Negative as well. Good. Any questions so far? So before in finite and in algebra, you guys did this part, but you never saw this, did you? The limit part? Because they were just trying to get you to do this, the mechanics. This is the easy part. Wait until the end to do that. If we do it right now, what's going to happen? Can we divide by 0? No, so if we shove this in right away, it's going to happen every time because we always divide by h. And if h goes to 0, and we do it too early, don't do it too early, okay? Let's wait. There's a time for every wait.
How did you get the x squared plus 5?
X squared plus 5, that was my original function.
Oh, okay.
Yeah, that was my f of x. So I'm just directly substituting that in. Okay? All right. So now I'm going to distribute this negative and do some stuff. Limit is h goes to 0 of x squared plus 2xh plus h squared plus 5 minus x squared minus 5 all over h. Can I cancel some stuff on the numerator? Can I get rid of some things? What? The x squared would be 5. Here's the hint, guys. Your entire original function should get canceled out. If it doesn't, there's something wrong. You did something wrong with your math. So I can kill the x squareds. I can kill the 5s. What's left?
2xh plus h squared.
Limit is h goes to 0 of 2xh plus h squared divided by h. Now, let's get rid of some h's. Is there one in every single term? So can we get rid of one in every single term? If I didn't have an h here, could I do that?
No.
That's right, you cannot do that. So let's,
Can
wait,
you
what?
back up just a little bit?
Absolutely.
I am just getting to the limit of h to 0, not top one.
This
So-
guy?
Yeah, so now you canceled out the x, like, x squareds
Uh-huh,
and the 5s.
uh-huh,
Oh, because it's like x squared minus x squared?
yeah,
Okay,
awesome.
alright, good.
That-
Why wouldn't you cancel out the H right away?
Wait, what?
Why wouldn't you cancel out the H in that middle step?
Right away?
Yeah.
Because it's pretty noisy. I mean, I could,
Okay, just for like,
but this has to happen before you cancel, because if you start canceling this first, there's nothing in every, there's no H in every term. So it really is a step-by-step-by-step thing. So I'm gonna cancel the numerator first, and then I'm gonna use the H and cancel the
You said
denominator.
something about if something doesn't happen and something's wrong.
If you can't cancel your entire original function, something's wrong. So your entire original function is located right here, and it all disappeared, so we're good. Now I'm just gonna kill those h's. What's left on the denominator? Denominator.
Oh.
It's not a 0, guys. Just wanna make sure. So now we have the limit as h goes to 0 of 2x plus h. You've gotten rid of the h on the denominator. Now you can plug h equals 0 in. And what's left? Okay, so f prime of x is 2x. Oh boy.
How did the power cancel out the square?
Okay, so let me rewrite this another way. So if I have 2xh plus h squared divided by h, let's pull an h out of the numerator. So if I pull an h out, what's left in this term?
Okay, I totally understand.
Okay, awesome.
Sorry.
That's okay. I want you guys to be comfortable with it, so.
So the only time that we put 0 into h is when there's only one h left.
When, no, not when there's one h left, but when you've gotten rid of the h on the denominator, which is the second to last step.
H on the
Yeah, there may be other h's left.
Okay, cool.
Oh, yeah, there may be other h's left. I just did a simple one. This is a simple one, guys.
Got it.
This is an easy function. Yeah. All right, let's try another one.
Okay.
Where the hell, I know, right? Woo.
Okay, and then lastly, how did you cancel out that h right there, 2x plus h?
I didn't cancel it. I made it go to 0. I actually put the limit in.
Oh,
Yep.
Well, it's not always gonna be 0, is it?
What, h?
Yeah.
Yes. Always. Because you're trying to make the distance between those 2 points smash together.
Oh, I see.
H is the distance between them, so we've got to take h to 0. It has to happen. Okay. So let's do another one. How about f of x equals 3x squared plus 5x minus 9. You've done this before. What's the derivative that we're looking for? Anybody know it?
3x plus h squared.
No.
how come the answer just stops at 2x?
Because that's the answer. You're done. You took the limit as h goes to 0. That was the whole point. Yeah, that's the derivative of x squared plus 5.
And that's a straight
Can you
line.
take a little on faith on this one? Because I'm going to show you at the end of today why it works that way. There's actually a shortcut, but I have to teach you how to walk before I teach you how to run.
So is 2x the
Okay.
derivative?
2x is the derivative, it is f prime of x. Yep. So we're looking for the derivative on this one as well. So remember, our definition is the limit as h goes to 0 of f of x plus h minus f of x divided by h. That's our goal. So we've already defined f of x, let's find f of x plus h. So we're going to substitute in x plus h wherever we see x. So we have 3 times x plus h squared plus 5 times x plus h, that's a 5, minus 9. Okay? And if you guys are comfortable with it, I'm just going to skip the whole foiling step and write it out. Is that okay?
Cool.
Cool? We've done that all before? Okay. So this is gonna be 3x squared plus 6xh plus 3h squared plus 5x plus 5h minus 9. I'll give you a second to write that down.
Have you done this before?
A few times. Like I said, I've taught this class for 9 years. Because I think it was my second year of teaching me through this app unit. I've been here for 10 years. So, done it a lot. Take that with a grain of salt, guys. It wasn't easy for me the first time. It's not gonna be easy for you the first time. It's okay. It is okay. I've got your back. You've gotta reach out to me if you get stuck. I'll be there for you. Okay? So that's my f of x plus h. So now I'm going to plug it into this formula up here. Limit as h goes to 0 of f of x plus h, and I'm going to parenthesize that whole beast. Minus my original function, which was 3x squared plus 5x minus 9. All over h. Hold on to the h, guys. Don't blow the h. Not ready. It's not yet. Not yet. So what do I do now? I'm going to distribute that negative sign, aren't I? Okay. So yeah, I'm going to write this all over again. And get rid of the parentheses because I don't need them anymore.
Cancel.
Right, Adam?
Ryan.
Adam?
Ryan.
You're Adam.
Ryan.
You're Adam.
Close.
You're going to be Adam now.
What if I don't like that?
Then you're Ryan.
Okay.
Sorry, Ryan.
No, you're good.
Ryan. Who's Adam? Is Adam in here? Is there an Adam? Hi, Adam. Hi, Adam. Adam.
Ryan.
I don't know how. Ryan. Adam. Ryan Adams? No. Didn't he turn out to be like an a-hole of a singer or something, like salts and lemon? Did you hear something about that? Ryan Adams?
I have no idea who that is.
Somebody's gonna Google it, I know you guys will. Somebody who's curious like me is gonna be like, okay. Ryan Adams assault. Ryan Adams charges. You're not. What cancels?
The 3x squared, the original function.
The original function, we're gonna get rid of the whole thing. Minus 5x plus 5x. Plus 9 minus 9. What's left? Some stuff. What stuff? I know, you said 6x. I'm just teasing you. Limit as h goes to 0 of 6xh plus 3h squared plus 5h. Anything else?
Nope.
All over h. Can I pull an h out of all of those terms up top?
Yeah, you can.
Hell yeah, I can. Freak yeah. You're so cute, like Colleen. Yeah, hell yeah, you can. Okay, so what does the numerator turn into?
6x.
Yes, so the limit is h goes to 0 of 6x plus 3h plus 5. The denominator goes to 1, so I can get rid of that. Now h goes to 0.
Now you plug in 0.
And what's left? 6x plus 5. That's the answer. Your derivative is 6x plus 5.
So would you write it like as the answer? Would you write like f with that little
F prime of x?
prime? of
Yes.
x? Write it like that.
Yeah, so this is what you would write, f prime of x equals 6x plus 5. Or you could write it like this, or you could, okay, so instead of just writing out all the ways I can say the derivative, why don't I just give you the page that says all the ways to say derivative? Yeah, and I've done this a time or two. All right.
But you only have to do one way, like, or
Yeah, but it's gonna show you a whole bunch of ways you're gonna need to recognize all of
A
them.
little bit.
So, good times.
I kind of regret not practicing it more.
No, well, she only gave it to us once,
Yeah.
so
It's kind of,
she would, yeah. And the class did not go as I wanted to.
no, not at
She's
all.
so much better.
Oh, yeah. She's like the best.
Yeah.
I was lost half the time in that other class.
Yeah, I was like, what are we doing?
Yeah, no. YouTube was my best friend in that class.
My friend was my best friend.
Wait, that's good.
Yeah,
Good
but
to
she
have
had
those
taken
friends.
calc, so.
Oh, really?
I'm like, yes. She
So
knew
you know-
everything, yeah. I was
They
like,
put you
yeah.
guys up, man.
I'm sorry, are you allergic to me?
So she doesn't need to take this class anymore? Or what?
Yeah, she has to, I don't know why. Oh, no, she's actually taking stats.
Yeah.
Yeah, so she's not doing business. I don't know why she took 1310. She's taking stats
I
now.
think she also teaches stats.
She does?
Yeah, I think so, because I saw in her office that she teaches like 2 other different math classes.
Oh, shit.
She's legit.
Yeah.
She's the real deal.
Honestly.
So many ways to say the derivative, aren't there? It's making its way across the bottom, but yes, Ryan.
This might be just like the worst question ever.
No.
What is
No.
the meaning of a derivative? Because I have never been explained that.
Okay.
And so it's just like this term that's flying around everywhere.
It is literally the instantaneous rate of change of any given function at any given x value. It is the instantaneous rate of change of any given function at any given x value. So for example, if I have a function that looks like this particular x has this particular slope.
Yes.
This particular x has this particular slope.
Yes.
This particular x has this particular slope. And there's an infinite number of answers. So it's some generic function that when you plug a number in, you get a slope out. Ooh, we're getting on to something else here. Yes?
So is the 6x plus 5 basically just the slope at that point?
Such a great question. No, but really close. Actually, it's really close because it's the generic function that allows you to plug any x in and get its corresponding slope out. So kind of yes, but not really. So let me show you what I'm talking about here in just a second. Yeah.
I was gonna say, so I guess what you're saying is that like if you plugged in whatever number for x in the x on 6x plus 5, you'll get the corresponding one.
You'll get the corresponding slope. If you do, shit, I erased it. Excuse my language, guys. Just slipped right out. It's my day. Remember, guys, if you plug an x into a function, what do you get out? Y. So if you want y's, you go to the original function. If you want a slope, you plug the x into the derivative.
Okay.
Plugging an x into the derivative gives you slopes. So let me give you some examples.
That makes more sense, thank you.
You're welcome.
Yeah.
It's the ability to test a slope at any
Yeah.
given point. Why do we care? I know a lot of you are like, okay, so how does this work in business world? Why do I care? We care because, can we see the future? Can we see the past?
Yes.
Yes. So can we use past performance to predict future behavior?
Yes.
Yeah, a little, within reason. So if this is our profit curve, are we expecting a crash anytime soon? No. But if this was our profit curve, what could be about to happen?
A peak and then drop.
A peak and then a drop, right? Do you guys see it?
Yes.
The next natural behavior for this is for it to top out and then start decreasing.
Oh,
You with me?
I'm with you.
We predict the future, the near future, using derivatives and using slopes. That's what this is good for, near future predictions. Does that help? Ryan,
Yeah.
let me erase some more of this. Ryan, what's your name? Oh, she's right. Yes.
So do they use the derivatives for like stock market?
Oh, yeah.
Okay.
Oh, yeah. All the time. So much. Is it accurate? Mostly. Stock market is an acceptable way to gamble with somebody else's money. A lot of somebody else's money. Because you give your money to some firm that manages your money and they go out and gamble with it. You choose your firm based on their reputation. Their reputation is their past performance. So if their past performance shows them a higher than average rate of return, you're gonna go with them, right? And if their past performance shows a lower than average rate of return, you're not gonna go with them, right? Math matters, guys. Math matters. It controls everything, including your retirement.
I thought you weren't cool with gambling.
That's
Yeah,
what
I
she
also
said,
don't wanna be
7.
eating SpaghettiOs when I'm 70. So, this is the truth. This is, like I said, who said that anyway, you snarky little. Got your number. No, this is an acceptable form of gambling, and there is some risk, obviously. Attend my 1080 lecture, and you will hear all about it tomorrow morning at 9:30 a.m. because I'm covering the stock market tomorrow. I do this for fun, you guys. It's so much fun. It's good. Okay, where was I? Oh yeah, 6x plus 5. What did I have? I had f of x equals 3x squared plus 5x minus 9, is that right? And you're like, wait, what? How did you do that? 6x plus 5. So the derivative was 6x plus 5. So if we take this function and we have this generic derivative good for all x, this will find slopes at any x value. I should probably not write and talk at the same time. At any x value that is on the function f of x. Okay? We'll find slopes at any x value that's on the function. So, good times. So let's see. What is the slope when x equals 3? When x equals 0? When x equals -1? So let's test all three of those. I just want to see what's happening with those x values. Is it growing? Is it shrinking? Is it staying stable? How fast is it growing? So what do? me plug some numbers in. F prime of 3 equals, plug and chug guys, 6 times 3 plus 5 equals 23. Okay? But I forgot to tell you something. Actually, I didn't forget, it was deliberate. Slope is still rise over run. This is 23 over what? 1. So we're saying, if I go from 3, x equals 3, to 1 over, which is x equals what? 4. If I go from 3 to 4, I can expect a rise of 23 in y. If we move from x equals 3 to x equals 4, we can expect a rise of y, a rise of 23 in the y direction. Let me illustrate this. Not tied to that function particularly. But let's just look at a function, some function. And let's say I take its derivative. And I want to test x equals 7. So that's x equals 7 along the line, right? Here's the line. Okay, so let's say the slope at x equals 7, the instantaneous rate of change gives us 10 over 1. So far, so good? So I'm just writing numbers out here, just making it up as I go along. So I'm saying if I go over 1 in my run, from 7 to 8, I can expect a rise of 10 in my original function. This is the trick. If you zoom in on this, those kind of mirror each other really close together, right? But if I go further away from my original point, x equals 7, what happens between my estimate and the reality? They get further apart. So the error, this error, starts growing, that's my error, starts growing the further away from my original point of reference I get. So that if I want to test somewhere over here, I'm not going to use 7 to do it. I'm going to back up 1 and use whatever this x value is to test it. Because I want to see what's happening in the near future, not the far future. You guys with me? Does it make sense? Give me a shaky if you're kind of there, but you're not sure. What?
Did you repeat that?
Yeah, absolutely. So notice that the error starts growing the further away from the point of reference we get. Our point of reference here is x equals 7. So if I want to be over here, hang on, if I want to be over here, I don't want to use x equals 7 as my reference point because my slope and my real function are going to be really far apart. I want to be somewhere in that region if I want to test over here. So I would back up 1 and test the slope right before the point I care about. Does that make sense? Because we always go over 1. Your slopes are always going to be divided by 1. So we're always going over 1 in x. Hold on to that, guys, because you're going to need it. Yes?
So if you're saying that, then why would you say we can expect it to be 23?
Because it's a prediction.
But if we know it's going to be different, then why would we predict that?
Because sometimes predictions are easier than the actual. Because what if we don't have all of this? What if 7 is the last point on our function? Then we need to be able to predict what's about to happen. So at the last point on our function, what's about to happen? We're predicting it's going to go up by 10. Now we're pretty sure that's going to be pretty accurate. Let me just show you how accurate. So we're checking on the movement between x equals 3 and x equals 4, is that right? Because we're going from 3 to over 1 to 4. We think it's going to be 23. Let's see exactly how much it's going to be. How do we test that? Put 4 into the original function and put 3 into the original function and then test the difference, right? Test the y values. So what's f of 4? That's 3 times 16 plus 20 minus 9, so that's what, 48 minus, or plus 20 is 68 minus 9 is, help me, 59, thank you. Subtracting I can't do, I can do everything else, but subtracting just eludes me. So 3 is 27 plus 15 minus 9. 27 is 37, 42 minus 9 is 33. Is that right? What's 59 minus 33? What was our guesstimate? That's pretty freaking close, you guys. And the thing is, when we work in the application world, when we work in the business world, these are gonna be even closer. They're literally gonna be pennies off, okay? So it's a great predictor of what's about to happen. Does that make sense? So this is the actual change from 3 to 4, from x equals 3 to x equals 4. Okay. What do you guys think? Yeah.
What if you picked a value that was on the decline?
Yes, you have to know where you're looking on your function. Because let's say you're predicting growth, right? And you just randomly pick one that shows a negative growth, you might freak the hell out, right? You might be like, oh my God, we're about to go into a recession, or we're gonna need to cut back production or something. We're gonna have to fire some people to stop our profits from sliding. But that's only good for that historical point. If the rest of the function is growing, you base yourself on the near past, right? But yeah, if we were to pick an x value over here, for example, you would get some negative slope, wouldn't you? Because that's literally decreasing, so there's gonna be some negative slope in that region. Did I answer your question or just totally jack it up?
I mean, I guess, but say that, so like, if that was x equals 7 where you already have
Mhm.
a mark, and then say on the downward slope it was like x equals 2,
Sure.
when you plug that into the f, I don't know, what is that little line thing called?
F of x or f prime of x?
Yeah, f prime of x, if you plug 2 into that, you're not gonna get a negative slope.
No, but this is not the same function as that over there. This is a completely different function. So this is just illustrative of what could happen on a function. This is a different function entirely. So just for giggles, just because you asked, let's graph this. Let's graph this. So grab your calculators. And let's see what happens. Let's make our x min, oh, I don't know, I'll graph it with you and we'll play with it. There it is. I knew it was here somewhere.
To graph that, you would still hit y equals, right?
Yeah, you'd still go to y equals, exactly. So 3x squared plus 5x minus 9. Graph. Yeah, your window may be crazy. Okay. So I want you guys to make your x min -6. Your x max 6. Your y min, let's make it -15. And your y max 15. And your scales should be 1. So -6, max 6, y min, -15, max 15. Is anybody struggling? Okay. What does it look like, guys? A U? Is there an actual technical name for that? Parabola. Good. It's a U, yes, it's a U. Is it an upside down U or a right side up U? It's a right side up U. So this is what it looks like. So that function looks like this. So this is 3x squared plus 5x minus 9. Okay, guys. equals 3. 1, 2, 3. X equals 3 is out here. So clearly, we're gonna have a really steep slope in the positive direction, right? It's growing and it's growing quick. How quick? We estimate it to be 23, it's actually 26. So it's even quicker than we thought. Is there a place where the slope goes 0? Where it bottoms out or tops out?
Yes.
Where?
Right at the bottom.
Right at the bottom. So some X value in the negative
Yeah.
region, right? Let's prove it. There's no H over KA or whatever the hell that crap was that you guys did in college algebra. No, we use the derivative now. If we plug X into a derivative, what do we get out? So if we set slope equal to 0, we could go the other way and solve for X, right? Let's do that. Set the slope equal to 0 equals 6x plus 5. Get the 5 over. Divide by 6. So negative 5/6 equals x. There you go. So the slope is 0, x equals negative 5/6. Isn't that freaking cool?
0 in for the whole thing because
Because this is
essentially
slope.
equals f prime of x.
Yeah, because this is slope, right? We're saying slope equals 6x plus 5, generic, good for all x. We're saying we need a specific slope of 0. What's the x that corresponds to that?
Yeah, but I mean, like, you didn't just put it in for that, for the x in parentheses, because f prime of x is, like, slope.
Yeah, f prime of x is slope. So, I'm sorry, what?
Sorry, I'm like kind of answering my own question.
Okay,
Yes,
that's cool.
I get it.
All right. So we have like 5 minutes left. Does this sort of make sense, guys? Kind of? That's kind of good. So I'm just gonna have you guys run this out. I don't know, pass it around. That'd be awesome. I have another one, and I'll hand this one out. So there's gonna be all kinds of paperwork flying. I told you guys I'm gonna kill trees. It sucks, but it's the easiest way to get you info. Welcome. 2, 4, 6, 7, 3, 7. Sorry, you're fine. 2, 4, 6, 7. Thank you. Welcome. 2, 4, 6, 7. I get that. Can you guys see clearly from the back? Am I writing large enough? Okay. If I ever write too small, just like give me a sign. Make it bigger. No one will see you but me because I'm up here and they're all in front of you, so it's all good. So there's 2 things coming around. The supplement to the notes that you just did on the board with me, but in a more formal manner. That's the fundamental definition of the derivative. Okay, the 9.3 handout. And then there's another one coming around called Let's Play Together in a Not So Creepy Way. I have weird names for my handouts. I don't know what to tell you. But basically, what I'm trying to show you guys on Let's Play Together is there is a physical, pretty relationship between a function and its derivative. And I'm going to show you exactly what I'm talking about with the last 5 minutes in class, because we're going to need it all. So I want you guys to understand the nature of the derivative. But to do that, you need to understand some pattern recognition. What's your highest power on your original function up here? Squared. What's your highest power on the derivative? What happened to the power? It went down by how much? 1. So this was a parabola. This is a line. So let's draw that one more time. We had, for this function, we had a parabola that looked like this, right? And and it was negative 5/6 is where it bottomed out. So if I were to draw its derivative right under it, see how that first page has the derivative right under it? So recall, this is x versus y. The trick here, guys, is the derivative is x versus slope. And this is subservient to the original function. Its entire reason for being is to describe the slopes on the original function. So we're graphing x versus slope, not x versus y. So the derivative is a line. What kind of slope do we have in this region? Negative. So it's positive y, 0y, negative y. Same thing here, positive slope, 0 slope, negative slope, okay? So we have a negative slope here. What kind of slope do we have here? 0. So this point is gonna be where your derivative crosses the x-axis, because this is where slope equals 0, okay? So we went from negative slope to positive slope on this side of that x, right? Positive slope. So magnitude of slope, is this really steep?
Yeah.
Yeah, steep negative getting less steep, less steep, less steep, it's approaching a 0 slope. Oh, it's 0 slope. Now it's getting steeper and steeper and steeper, going away in magnitude from 0. You guys with me?
Yep.
Here's your derivative. It looks like that. If you were to graph 6x plus 5 and 3x squared plus 5x minus 9 on the same thing, this sucker would cross right here and it would just overlay, just like that. Because the place where your function bottoms out here is the place where the slope is 0 here. You guys cool with that? Yes?
On a function that would like have two, like, that looks like this on here, would there be two derivatives because there's a top and a bottom?
Well, there would be two places where the slope is 0, so flip it to page 2 to look, because I actually showed the solution on page 2. So you went from a cube, which was what that first function was, down to a parabola, right? So far, so groovy? So it's gonna cross the x-axis at 2 points, and that's where the slope is 0 on the original function. So this guy, I'm gonna draw it on here. So I can say, and I know we're right out of time, so hang tight, guys, I know you're getting restless. 0 slope here, crossing the x-axis here. 0 slope here, crossing the x-axis here. This is a negative slope down here, so it's gonna be somewhere down here, right? Positive slope here, so it's gonna be somewhere up here. Positive slope up here, it's gonna be somewhere up here. This was a cube, this has to be a parabola because the power goes down by 1. That's the pattern. That's a crappy parabola, but you get the idea. Do you guys see it? It's easy, isn't it? The concept is difficult, it's gonna take time. You guys don't have any formal homework this weekend. It's a long weekend because no homework and no class on Monday, so you get a break. But there's a downside to that. I want you to read these handouts. Just read them, just skim them. That's all.
Are we gonna have practice problems over in this though?
No. Because I'm not gonna make you guys do